a cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit and is placed into a 35-degree refrigerator. After 10 minutes, the cheesecake has cooled to 150 degrees Fahrenheit. If we must wait until the cheesecake has cooled to 70 degrees Fahrenheit before we eat it, how long will we have to wait? Let's solve the problem together. Here is the Newton's law of cooling. The temperature of an object T in a surrounding air with temperature T sub S will behave according to the formula T of T is equal to AE raised to KT plus T sub S, where small letter t is the time in seconds, A is the difference between the initial temperature of the object and the surroundings, and K is a constant, the continuous rate of cooling of the object. So to solve our problem, let's begin with the formula, which is the Newton's law of cooling. From the given problem, we know that the cheesecake is placed in a refrigerator that has a temperature of 35 degrees Fahrenheit. This 35 degrees is our T sub S. This is the temperature of the surroundings. So we are going to replace this T sub S by 35 degrees. Also, it is given that when the cheesecake is taken out of the oven, that means time is equal to 0, the temperature is 165 degrees Fahrenheit. So that means we can now replace this T of T by 165 degrees Fahrenheit, and that happens when time is equal to 0. So let's do now the substitution. So we now have here 165, and we are going to replace this T by 0. And then let's simplify this equation. K times 0 is equal to 0, and any number raised to 0 equals 1. So we now have this part here equal to 1. And then we subtract 35 from both sides. We have the value now of A equals 130. This 130 will now be substituted to our equation. So we now have this equation. Then from the problem also, it is given that at T equals 10 minutes, the temperature of the cheesecake is 150 degrees Fahrenheit. So we now do the substitution again. We replace time by 10 minutes, and our T of T becomes 150 degrees Fahrenheit. So we now have T of T equals 150 and T equals 10. And simplifying now this equation, we subtract 35 from both sides to get 115 and multiply K times 10 to get 10K. And then dividing both sides by 130, we arrive at this result. And then let's take the natural logarithms of both sides to get now this line. ln of the left side is equal to ln of the right side. Applying now the power rule of logarithms, you can now place this exponent 10k as the coefficient of ln of e, and then since ln of e is equal to 1, we now arrive at ln of 115 over 130 is equal to 10k. And then dividing both sides by 10 and applying the symmetric property of equality, we now arrive at k equals negative 0.0123. This is now our value of k that we can substitute to the formula. So from this formula, replacing now k by the value that we just arrived at, negative 0.0123, we now have this formula. This is now easy to compute because we only have two variables left. We have the variable for small t, which is the time, and we have the variable for the temperature. Our target temperature is 70 degrees Fahrenheit. So we can replace this by 70. We now arrive at this equation. Instead of T of T, we have 70. And from here, we can now solve for T. First, we subtract 35 from both sides to get 35 equals 130 e raised to negative 0.0123 t. And then we divide both sides by 130. And then we take the natural logarithms of both sides to arrive at this form, applying the power rule also of logarithms. And then finally, solving now for t and applying symmetric property of equality, we now arrive at t equals 106.68 minutes, which we can round off to 107 minutes. So for our final answer, it will take about 107 minutes or 1 hour and 47 minutes for the cheesecake to cool down to 70 degrees Fahrenheit.